Okay, so I'm going to talk briefly about this chapter right here. We're starting sort of a new section, and so that means there's a lot of new terminology, but hopefully not a whole lot of new processes. I'm going to go very quickly through some of the introductory stuff because you can kind of look at that on your own and then spend most of the time on some of the practice problems in the second half. So we're talking about electricity here, which is really just a new force, right? That's really the core of what we're going to start with here, right? We're talking about forces. That means free body diagrams, F equals ma is going to be involved. And so the electric force comes from when you have the presence of charges, right? The gravitational forces we've learned talks is sort of when you have mass, you have a gravitational force. The electric force is when you have charges. And so this, right, first bit is we need to figure out the model. And this is the part I'm going to go through kind of quickly and just talk about the summary. And then if you have questions, you can ask later, or you can flip through the slides and sort of see the examples yourself. Okay, so the first couple of slides are just sort of showing you experiments that you could do if you had sensitive enough equipment and sort of careful enough tools. And in fact, if we were in the classroom, you would be doing some of this stuff. But obviously, we're not going to do that. So I'm going to jump ahead a little bit. And just get to the conclusions. So this is sort of the model that we're going to use. And it's really important to sort of recognize, because this is sort of the fundamentals of where charge comes from. So understanding this gives you the tools that you need to sort of explain why something happens. Not a mathematical calculation, but a written explanation. So the first thing is that a lot of what we're going to do involves friction as the method to produce, or in this, to be more specific, move charge around. So if you see something that describes a problem as things are rubbed together or rubbed against one another, that's a way that you can create a charge on something. This next statement, right, two kinds of charge, should be something that you kind of already know, right? Positive charge and negative charge. And then similarly, right, like charges repel, opposite charges attract, right? So a lot of that should hopefully be familiar. A couple other things. This electric force is a long range force. It's like gravity. It doesn't require contact. Right? The electric forces we'll see is very, very similar to gravity. Many of the practice problems we're going to do are going to remind you of some of the ones we did in the gravity chapter. These next two are very important and should be familiar to any of you that are taking or have finished chemistry, right? Everything has charge on it. The process of charging is about transferring, not creating charge, right? Electrons are specifically what moves. We'll see that in another couple slides. And this last statement is absolutely critical, right? Charge is conserved. You can't create or destroy it. You can just move it around. This type of thing comes up a lot on multiple choice or sort of experimental analysis in sort of free response questions, right? What went wrong with the experiment? Oh, well, you have less charge than you started with. That's impossible, right? Something like that. So you definitely have to remember, right? Charge, all this process of charging is really about transfer, not creation. Okay, another couple examples. Some more terminology things, right? There are two types of materials that we're going to deal with, and you have to know these terms, right? Vocabulary terms: conductors and insulators. In both cases, right, both of these materials are things that can hold charge. The difference between them is how charge moves, right? If I put charge on an insulator, it stays there. It stays where I put it. If I put charge on a conductor, it can flow anywhere else in the conductor on its own and frequently will. Right? So conductors, charge moves. Insulators, charge is wherever I put it. I can transfer charge to both. I can transfer charge from both. Okay. Another terminology, right? Electrostatic equilibrium, right? If I put charge on a conductor, the charge will flow around until it stops moving, right? The net force is zero. Equilibrium is still, right, F net equals zero, right? So electrostatic equilibrium is saying there's no electric force left. So all the charges move around until they're stationary again, right? Conductors, the charges will move until they're in equilibrium. We'll see more examples of that later. Um, So here's a type of question that you might see, right? Two objects. Object A is charged, object B is uncharged. Can you tell me anything about whether those are insulators or conductors? The answer to this is no, right? Both the objects can hold charge, right? This is the right one. Both the objects can hold charge, but conductors and insulators are about transferring charge. I didn't tell you anything about the transfer or flow of charge. So it's got to be E. Oops, one too far again. All right, so you already saw the answer, but let's read the question, right? We have a charged object, right? So we're going to have an electric force. And we know there's another object that attracts. And so your first instinct might be to say, well, an object that attracts the glass rod must have the opposite charge of the glass rod. And that is a possible explanation, but it's not the only one. And that goes back to this concept right here about this electrostatic polarization, right? This right here is an object that has no net charge, but the charge is unevenly distributed. It's polarized. And so it's possible that your object could be a neutral, right, no net charge object and still attract it, right? So we don't know what it'll do to the plastic rod. It might repel it if it's the same charge, but it might attract it if it's neutral. So it's got to be D. Right? Here's another very similarly example, right? We know that this is positive. So this rod right here, we want to sort of ask, what is it? Well, there's two options. It could be negatively charged, right? That would be negative charge, opposites attract. Great. But it could also be a neutral object that's been polarized, right? That would be a neutral thing and it would still attract it. And so it's either B or C, and that's option E, right? This type of question comes up a lot on multiple choice, right? It's a very, very important trick to remember that neutral and polarized objects can still attract things through the electric force. All right, skipping some of these. So here's another good sort of question, right? We have identical metal spheres that are charged, right, as shown in the picture, and we do a couple steps, a couple processes. We have to figure out what it looks like at the end. So the first thing we do is we touch charge or spheres P and Q together. And these are metal, right, which means conductor. And that means charge can flow, right? That's the important bit of the metal. So if we touch those spheres together, what's going to happen? Well, because they're conductors, charge is going to flow, right? The positive charge on P is going to want to go over to Q, and the negative charge on Q is going to want to go over to P. And the condition that the charge sort of stops flowing is that electrostatic equilibrium condition, which is when they have equal charges. So the total charge on this is 4 plus a negative 2, which is 2 nanocoulombs, which means each one will have 1 nanocoulomb after that first step, right? Then we do step 2, right? Step 2, we touch Q and R, right? If we touch Q and R together, now we're doing 1 and negative 1 nanocoulomb. And once again, they're both metal, so they're going to flow into equilibrium. We have 1 plus minus 1 equals 0 nanocoulombs. And so they're both going to be neutral, right? This type of thing is sort of understanding how charge moves around and sort of what equilibrium means is really important, okay? So it's also important to note that I haven't actually talked about the fundamental thing that causes charge. That's the next section, right? Notice how in here I said, right, the positive charge moves from P to Q. That is mathematically true, but it's not really true. And that's what we're going to see in the next section here. And again, really briefly, this is really chemistry, right? So you should remember this from your chemistry class, right? Where does charge come from? It comes from the properties of atoms, right? Protons in the nucleus are positively charged. Electrons that surround it are negatively charged. And because the electrons are the more free to move, it really is negative charge that moves. But mathematically, it doesn't make a difference whether we say like electrons go to the left or positive charge goes to the right. It's like two negatives that cancel out, basically. Okay. The important message in this section is really this table right here, right? You need to know the properties of protons and electrons, right? Why does the mass matter? Because we're going to be doing F equals ma a lot, right? Protons and electrons have different masses, which means if they feel the same force, they're going to accelerate differently. However, notice their charges are exactly the same magnitude but opposite sign, right? And also the unit for charge, right, is this thing called coulombs, right? Coulombs is our unit for charge. Okay, all these values in this table are on the AP equation sheet, so you don't have to memorize them. But this is a handy table to refer back to. Also notice we're going to be representing charge with Q. Actually, that kind of covered it up, so let's move that down here, right? Q is what we're going to use for charge, either capital or lowercase. The other thing is that this letter and this value has a very important meaning. It's called the fundamental charge. And it's a little bit special because you can't have a fraction of it, right? You either have a proton or 2 protons or 3 protons. You can't have half a proton's worth of charge. There is nothing that has a fraction of E of a charge, right? So if I ever tell you that something has, say, like 1.3 E of charge, you immediately can say, that's impossible, right? That can't be true. It has to be 1.0, actually, I shouldn't even write a decimal. It has to be either a 1E or 2E, right? No fractions, right? You can't have fractions of that fundamental charge. Okay, and so now we're going to jump to sort of how to calculate some stuff. We've gotten through some of the concept stuff here. There is more chemistry things in there which are worth looking at, but you've probably seen that already elsewhere, I hope. So this is the core of what we need to get out of this section, is Coulomb's law. Okay, so what we talked about so far is the model, right? The descriptive nature. If I ask you to write a paragraph about how charges and electric forces work, the first 2 sections will tell you that. But it won't give you any numbers, right? It won't tell you, oh, the force is a certain amount, or, the acceleration is a certain number. What we need to actually calculate a force is what's called Coulomb's law. Just like we had Newton's law of universal gravitation to calculate the force due to gravity, we have Coulomb's law to calculate the force due to electricity. Okay, so if you see Coulomb's law or electric force, it means the same thing. So I'm just going to state it. Right, we've kind of tested some of or if you go back to the first couple slides, you would see some tests that sort of justify why this might be true. But this is Coulomb's law right here. And notice that it is very, very similar to Newton's law of gravity. Right? Newton's law of gravity was this. Right? Notice it's very, very similar. There's a couple small differences. Right? Instead of the gravitational constant, you have this K, which is the electrostatic constant, which makes sense. And instead of masses for gravity, we have charges for the electric force, which makes sense. But the r squared in the denominator is the same, right? They're the same type of force in that sense, the inverse square idea. And so a lot of the reasoning that we did with the gravitational force, you should be able to do with the electric force. That's a really handy thing to keep in mind. Right, the value of K is right here. It's on the AP sheet. Coulomb's law is on the AP sheet, so you just have to remember how to use it. Notice as well, right, action, reaction pair. If I have 2 charges, they must feel equal magnitude forces from each other, but opposite direction. Okay. So, right, I'm going to use K as 9 just because that's a lot easier. But, if you want to be more precise, put in 8.99. Notice as well, right, this is a force, right? Coulomb's law calculates the magnitude. The direction, we already know, right? If the two charges are the same sign, it's a repulsive force, and if they're opposite, it's attractive. Right? The other thing to note is, right, Coulomb's law applies specifically to point charges, which is all we're going to really deal with in this class. So don't worry about any exceptions to that. If you take AP Physics 2, you'll see some exceptions. But for now, you're only going to deal with point charges. The last thing to note, right, is Coulomb's law is just another force, right? It really isn't special. And so that means that you can calculate net forces by adding up the vectors, just like we've done. And you can add any other type of forces too. You can have a net force that's based on an electric force and a gravitational force and a frictional force. That would be fine, right? Electric forces are just another force to use. And so that means free body diagrams are going to be critical because you'll just draw that force in there just like any of the others. And then you can calculate with Coulomb's law. Right? So notice, right, visual overview, right? That means free body diagrams. When you deal with problems involving Coulomb's law, free body diagrams are a great place to start. Right, and then the rest is just kind of reminders about vector math. So let's do some practice because that's really where we're going to get most of the value. So we have a picture here, right? Charge 2 and charge 1. Charge 2 is twice the charge, and we're told the force of 1 on 2 is this. Well, look at the wording, right? This is F1 on 2. We want to know the F2 on 1. That is a Newton's third law statement, right? And we know what Newton's third law says. It's equal magnitude and opposite direction. So that means it has to be equal magnitude and opposite direction, and that looks like choice B to me. Notice that even though the charges are not the same, right? Charge 1 and charge 2 are not the same. The forces are. Why? Because Coulomb's law says that it's the product, right? The product that matters for both of them. So charge 2 being bigger makes the force vector bigger for both, not just for charge 1 or just for charge 2, for both, from the Newton's third law. Right? Nothing different, just a different force to apply it to. Right? Okay, so now, right, we have the same situation, right? Charge 2 is twice the magnitude of charge 1, but now we're going to change the distance. Right? So we want to know what happens to force 1 on 2. That's how does this force change if we cut the distance in half? Well, let's look at the equation. Right? There's our equation. So if r is divided by 2, then r squared turns into r squared over 2 squared, or 4. And it's in the denominator, so that means that we're dividing by 1/4, which is the same as multiplying by 4. So our force should be 4 times as big. Right? So we're looking for a vector that is 4 times as long as this one. So A is shorter, that's clearly out. B is the same length, that's clearly out. C looks to me like it's about twice as long. That's not 4 times as long. So it's got to be D. We're looking for something that's longer than any of those. Right? And so they draw roughly what that would be. Again, this looks a lot like a gravity problem, hopefully. Okay, so here we have 3 situations, and we want to know which is the biggest force. Right? So we just have to apply Coulomb's law. Right? So this one is going to be K capital Q lowercase q over r squared. This one is going to be K capital Q 2q over 2r quantity squared. This is going to be K capital Q 4 little q over 2r squared. Right? And then all we need to do is simplify. So for this one, right, we have a 2 and a 2 squared. That's a 1/2. Right? This one we have a 4 and a 2 squared, which just cancels. So it's just KQQ over r squared. And now I can compare. And I see that here's a 1/2, and these don't have anything in front. So this one is the smallest, and the first and the third are tied, and that looks like option E. right? Okay. Moving on. So our next one, we're going to place a charge on the black dot, right? Whatever magnitude it is, we don't know, but I'll just call it capital Q. And we want to know which is the force the largest. So we're just going to call it capital Q. As long as it's identical, it doesn't matter because we're trying to compare, not get an exact number. So this one, right, just plug it in. KQ capital Q over R squared. K2Q capital Q over 2R squared. K2Q capital Q over R squared. KQ capital Q over 2R squared. Right, and again, we simplify. So this, we have a 2 and 2 squared in the denominator. That's a 1/2. In option C, we just have a 2 in the numerator. In option D, we have a just 2 squared in the denominator. Right, and so now I can see by comparing the coefficients, right, that's the biggest. So it should be option C. And sure enough, there we go. Okay, so now a little bit harder, right? Not a lot, but a little bit harder. So now we're going to put, and again, an identical charge, right? And all the charges shown are the same magnitude, right? So we can kind of do this actually with vector drawing, right? Now we have 2 electric forces. There are 2 interactions that are extra charge fields. There's this interaction, and there's this interaction. And so the force is going to be the vector sum of those 2. So for option A, for example, say we put a positive charge here, it's going to feel an attractive force that way, and it's going to feel a repulsive force from the red one, right? And those 2 vectors are going to be equal length because the magnitudes of charges are the same, and clearly in the picture the distances are. I don't know what the numbers are, but those 2 arrows have to be the same length. So for option B, if we put a positive charge there, we have the blue interaction and the red interaction. From the blue interaction, we are again going to get an attractive force, but from the red one, we're going to get a repulsive one. And in this case, because the positive charge is twice as far away, it's going to be 1/4 of the force. So I need to draw this very short, right, about like that. And the blue arrow, right, these should be the same length, right, because it's the same magnitude of charge. Option C, we have 2 interactions again. So with the blue interaction, it's a repulsive force, and it's got to be the same length as sort of my original vectors in A, so about like that. And the red interaction is repulsive as well, but very short, right? That's a little bit too long, actually. It's very hard to draw 1/4. Let's see if I can get that. More like that, right? Very short. And then D, once again, 2 interactions. We draw the force vectors for both. The blue interaction is attractive, and it's the original length. The red interaction is also attractive and the original length. So the magnitude of the force is the largest. Well, I can see very quickly that D is out. Those 2 vectors are going to cancel. That's no force. That's got to lose. If I compare B and C, I can see that B and C has to be bigger, because in B there is some cancellation, and in C there's some in the same direction, so B is out. And now if I compare A and C, I see that in A we're adding 2 of the sort of long length vectors, and in C we're adding 1 long and 1 short, so A has to be bigger than that, which you probably kind of saw from the beginning, but spending more time on it is fine. Right? So same process for like free body diagrams and superposition of forces here. Okay, so another question here about net force, right? So charge minus Q. The negative charge, this interaction, is going to be a repulsive force. Let's see if I can draw that on there, right? Repulsive force. The positive charge, this interaction, is going to be an attractive force. But because the positive charge is farther away, we know the repulsive force from the negative charge has to be bigger. And that means the net force has to be to the right. Okay? So this question here, right, read it carefully, but it's a little more confusing than it might look at first glance, because it doesn't tell you a whole lot, right? We're given a position and a charge, and we measure a force. So I'm thinking already that we have to do something with Coulomb's law, right? And so the question is, are there any issues with this? And the first question is, well, I mean, you look at it and say, well, how do I know, right? I don't know what happened. Is there friction involved? Who knows? But I can see that if I look at this equation, right, I know the force. I know K because it's a constant. I know R, and I know one charge, right? I know one of the charges. I could find what the other charge has to be. So I'm going to do that and see if that gives me any additional information. So I plug in the values for the force, the distance, and K. Notice that the distance has to be in meters. This is 1 times 10 to the negative third meters. You have to work in SI units. So if I plug all that in and solve for Q2, I will find that Q2 is 2 times 10 to the negative 19th coulombs. And now we're getting somewhere, because if you remember, the fundamental charge, E, is 1.6 times 10 to the negative 19th coulombs. So that means that if that force sensor is correct, charge Q2 has to be 1.25 times the fundamental charge. And this is a problem, because that means that something is wrong. This can't happen. You can't have a fraction of the fundamental charge. It's either E or it's 2E. You can't do that. And so there has to be something wrong with his result. Maybe it's a procedural mistake. Maybe there's friction involved that he neglected. Maybe it's a calculation mistake that his force sensor is calibrated wrong. But something is clearly not right, because you got a result that's physically impossible. Okay, so our next example here is a net force from 2 different pictures. And really, from this paragraph right here, you should, as a first step, make these 2 drawings, right? That's really the problem you have to do. Everything else is just plugging numbers into Coulomb's law. The one thing to note is there is a typo, right? This should be minus 10 nanocoulombs. That's what the picture shows, right? It was already a positive. So from that description, right, we draw a free body diagram, and then it's just a matter of calculating it. And they do all the steps, so I'm just going to kind of flip through it, right? So they've done their free body diagrams. They can use Coulomb's law to calculate it. If I had a slide that would load, yeah, there we go, right? So they calculate it. Notice that the magnitude is going to be the same for every single force vector, right? All 4 of these have the same exact magnitude. The direction comes from knowing that positive and positive repel, positive and negative attract. So the first picture is clearly 0 net force, and the bottom picture, you take the thing and just double them. Okay. So, right, this is just now an example that was not done for you as much. So we have a charge here and a charge here. This is 4 nanocoulombs. This is negative 1 nanocoulombs, and this distance is 1.0 centimeters. And we want to know the magnitude and direction. Well, the direction is easy, right? It's attractive, right? They're opposite charges, they attract, right? The net force is going to be like that. The magnitude comes from Coulomb's law. So K Q1 Q2 over R squared, right? So we plug those numbers in, 9 times 10 to the 9th. Many, many times we're going to be dealing with nano as a prefix for charges. Nano is 10 to the negative 9th. And I'm out of space, so I have to sort of go down here. Right? And that's all over the separation distance squared. again, you have to work in meters, so that is 10 to the negative second squared. And if you plug that into your calculator, you will get 3.6 times 10 to the negative fourth newtons, right? And so we've got the magnitude and direction. Okay, so a bit more vector math, right? There are 3 interactions, right? And each interaction has its own electric force. So we can draw the 3 individual forces, right? From the top charge, right, there's this force. From the side charge, there's this force. From the diagonal charge, there's that force. If I take those 3 vectors and add them up, right, head to tail, right, my vector sum points like that, which is option B, right? I didn't need to actually use Coulomb's law. I just had to do vector math and remember that opposites repel, right? Same idea here. So now the interaction with the positive charge is going to be a net force this way, repulsive. The interaction with the negative charge is going to be a net force that way, attractive. Those 2 vectors have to be the same length, right? This distance is the same for both. And so if I add those vectors up, right, like head to tail, I'm going to get horizontal, which is D. Right? Vector math. We haven't done that for a little bit. Okay, so here, this one is again where if this was a real AP problem, this would all you'd be given just to be the paragraph most likely. So let's look at that before we go to the drawing, right? So the question here is asking, will the glass bead leap up? And that is a comparison between 2 different forces, right? If the electric force is stronger than the gravitational force, then the net force is upward and it leaps upward and sticks to the plastic. And if the weight force is bigger, then the net force is downward and just sits right on the table, right? And so that's what's drawn right here, right? The free body diagram for the charge. There are 2 forces that really matter, the electric force and the weight. We need to calculate both and compare because that tells us what the net force direction is. And that is what they do right here, right? They calculate the electric force using Coulomb's law, right? 10 to the negative third, and the weight force. And it turns out the electric force is bigger. That tells us the net force is upward, so it will leap upward. In fact, with this information, you could calculate the acceleration and tell me sort of how fast it goes upward, but that's not what's asked. A similar problem, right? Comparing this weight and gravitational force idea. Notice this amount of charge, right? Picocoulomb. Pico is a relatively rarely used prefix. This is 10 to the negative 12th. Right, that's a very small amount of charge. But the humming bees are very light, so let's compare these 2. So the weight is mg. Remember, mass has to be in kilograms, so that's 0.1 times 10 to the negative third kilograms, and times 9.8, right? So this is going to be 9.8 times 10 to the negative fourth newtons. The electric force is Coulomb's law. KQQ over R squared. And so now we just need to plug it in, right? 9 times 10 to the 9th, K. 23 picocoulombs is 23 times 10 to the negative 12th, and they're both that charge, so we have 2 of them. And then R is a centimeter, so that's 1 times 10 to the negative second meters. And if you plug that in, you get a quite small number, which is 4.7 times 10 to the negative 8th newtons, approximately. If I can remember right, that might be a 9. But it doesn't really change the fact, right? Clearly, the electric force is much smaller than their weight. And that's kind of representative of everyday life, right? We don't notice electric forces most of the time because we don't have very much charge on us, right? Picocoulombs are small amounts of charge. Okay, so here we have a plastic ball sort of suspended above another, right? And so to understand why, right? Well, charged, right? So what forces are acting on this top ball? We have a weight and an electric force. And for it to be suspended, right, equilibrium, that tells us those two are equal. So if the charge is doubled, right, which of these forces changes? Right, if the charge is doubled, that force is going to change, but the weight doesn't. And so that means that we need to find a new position such that the electric force is unchanged, that it stays in equilibrium. So the electric force originally is KQ1 Q2 over R squared. If we double both charges, then we have K2Q1, 2Q2, right? Which is a factor of 4 in the numerator, right? So this factor of 4 is the problem. We need to get back to the original force, which means we need to get a factor of 4 in the denominator. And that means that R new has to equal 2 R old, because 2 squared is 4. Right, and then the factor of 4 in the numerator and the denominator will cancel, and then the electric force will still balance the weight. So it should be twice the distance, 2d. There's the answer. Okay, this is another, right, multiple correct options. And this one deals with applying F equals ma in addition to Coulomb's law. So, right, we have an electron, we have a proton. They're released from rest, they move towards each other. So the first thing we note is that, right, electrostatic attraction, right, forces are the same, right? The force on the proton and the force on the electron must be the same by Newton's third law. But that does not mean their accelerations are the same, right? Since F over m equals a, and the electron is much less mass, the acceleration of the electron has to be much greater than the acceleration of the proton, right? The forces are the same, but the motion isn't. So looking at options A, B, and C, right, those are all mutually contradictory. One of those three must be true, but only one. And so if we know the electron has a bigger acceleration, that means it's going to travel more distance. And that's option B, right? They don't meet in the middle because the electron travels faster, right? The electron covers a bigger distance. So, same speed. Is this possible? Well, no, right? If they have different accelerations, they can't have the same speed. That one's out. And then option 3, this one, or option E, right? That violates the third law, right? So it's just B. Okay. So this one is it's kind of a chemistry question, but I put it in here because I think it really helps illustrate how the electric force compares to the gravitational force. So we have a small amount of hydrogen, right? 1 mole of hydrogen. 2 grams, right? Not very much at all. We're going to take all the electrons away from that mole of hydrogen and put them on the other side of the Earth. And we're going to ask the question, what force is then happening between the electrons on one side of the Earth and the protons left over from the hydrogen on the other side of the Earth? So the first thing is to figure out how much charge that is. Well, a mole of hydrogen, H2, hydrogen has 1 electron, which means H2 has 2 electrons. So if we have 1 mole H2, and this should look very familiar to you that are in chemistry, then we have 6.02 times 10 to the 23rd. Let's go with molecules, right? That's Avogadro's number. And for every 1 molecule of H2, we have 2 electrons, right? But we also know that for every electron, how much charge it has. That's the fundamental charge. So 1 electron, 1.6 times 10 to the negative 19th coulombs, right? That's all I did right here, just some unit conversions, basically. So we cancel some units. And if you plug all that into your calculator, you get a pretty large amount of charge. you should get something like 1.92 times 10 to the fifth coulombs of charge. Now remember, most of the problems we've done so far were like nano coulombs, 10 to the negative ninth. This is almost a million coulombs. So that's a lot of charge. Now, what force do we have? Well, let's calculate that. So K, Q1, Q2 over R squared. So K is a constant, that's not changing. Q is the charge of the protons, which we just found. And the charge of the electrons is the same magnitude but the opposite sign, right? So that's the interaction we have. And then the distance, R, is the diameter of the Earth, right? So that is 2 times 6,380 times 10 to the third squared, right? Because I have to convert to meters. And so if you put that into your calculator, you are going to get a pretty big number. Right, even though the radius is quite large, the amount of charge is very large. And so you end up getting that this is roughly 2 times 10 to the sixth newtons. Right, that is huge. Right, that is a huge force. That is 2 million newtons of force just from the electric charge sort of contained in 1 mole of hydrogen. I hope that illustrates really how strong the electric force is relative to the gravitational force, right? If I took, say, 1 mole of mass and put it on the other side of the Earth, the gravitational force between that mass and me would be microscopically small, right? Like unmeasurable. But the electric force is immensely strong. And so that's kind of an important thing to keep in mind, is that's why usually electric forces involve such small charges, otherwise the forces are just huge. And so that kind of is the summary of sort of this electric model and electric forces, and hopefully that gives kind of a starting point here.